Hello and welcome to another finite element lecture. In this lecture we are going to learn about failure analysis. So far we have used finite element modeling to predict stress distribution across our domain, our structure. Now we are going to learn how to use this information in order to predict if the structure will fail under the given loading or not. At the end of this lecture, you will be able to choose suitable failure criteria for different materials, explain the concept of fatigue failure, and use the SN curve for fatigue analysis. Well, why do we need to know about this? Failure can occur in structures due to combined stresses. For example, the neck of a hip prosthesis is subjected to stresses produced by bending, compression, and shear. And these are the type of loads that hip is usually subjected to in daily life. We need to incorporate these stresses produced by these different loads when we are designing the prosthesis. Also, an estimated 50 to 90% of all mechanical failures occur at stress levels which are well below the yield strengths of the material. These failures are caused by cyclic stresses or loading, and we call this type of failures fatigue failure. An example is the front wheel of this tandem bike. These athletes are practicing for Paralympics 2008. So fortunately both athletes were fine and they went on to win the gold medal. So really as designers we should design structures that do not fail in their intended lifetime. So let's look at this bar. This is like standard tensile test. We are applying a force that is pulling this specimen on opposite sides. You know, this is the type of experiments we do with instrument machines. We can zoom into one point within our domain and extract that infinitesimal element out of it. So if I extract an element, let's say from a region like this, that element in 3 dimensions is often shown with a cube. We call this an infinitesimal element. You shouldn't mix this with finite elements. So this is a mathematical definition of a point within our domain which has volume. So as I mentioned, this is a cube. And now we can look at different faces of this cube. So you know the force is applied in this direction. So if we use our coordinate system like x, y, and z, then force is applied on the z direction. And you know if the cross-sectional area here is A, then here on this face of our element we have stress, a normal stress that is force divided by the area. And of course this element has to be in equilibrium because our structure is in equilibrium. Therefore on the opposite face, on the other side, on the bottom, we have the same amount of stress, which is F divided by A. So I'm sure you're familiar with the concept of normal stress this way. Now if you look at this experiment, this is a standard shear test where you see that these forces are shearing our rod. So again, if I zoom into this region and take an infinitesimal element out of that region, then that element, again, we represent it with an infinitesimal cube like this one, right? And here we have a force that is applied downwards. So on this face of our element, we will have stress that is a shear stress. So that stress is within the face here, and it is parallel now to the z-axis. Okay, so if we take that one, so this stress will be like this because our force is working downwards, and the amount of this stress is force divided by the cross-sectional area, right? So if we call this cross-sectional area A, but you know that our element, our structure is in static equilibrium, therefore we have to have another stress or another force on this face on the bottom that is passing through this edge. Therefore the moments are zero when we look at the free body diagram. So that one, I can show it with that. So this is as well tau, which is F over A. So this is the shear stress applied here. But you know that this element is not moving in Z, in Y, or in X direction. So in X, we don't have any forces. But in Z and Y, we now have this force or this stress and this stress. Therefore, there have to be other stresses that are balancing these two. So one has to be this way and another on this face should be working upwards. So these two cancel each other and these two cancel each other. So this way you can see the definition of the normal stress and shear stress by using this infinitesimal element. So now let's look at our infinitesimal element under the most generic loading condition. So we can have normal stress on each face. So in X direction, on this face we have sigma X. On this face we would have sigma Y. So this is normal stress due to the force in Y direction. And here we can have sigma Z. And then we have shear stresses as well applied on all these faces. So on this face, which is an X face, we can have a shear stress that is aligned with the y-axis. So we call this tau xy. And as you remember, if we have this one, we have to have another shear stress on this face that will balance this one. So that's tau yx, which is equal to xy. So again, I use tau xy here, which is equals to tau yx. And on this face, you can also have a shear stress that is along the z-axis. So it will look like this. And this one, we can call this one tau xz. And then we should have another one on this face, which is equal to this one and pointing to the same edge. So that would be tau xz, which is equal to tau zx, right? So this is a z face and stress in x direction. So that's tau zx, but we know due to equilibrium, these two are equal, tau xz and tau zx. As well as this face, if you look at that one, so that is a y face. So here you can have tau yz, and here you can have tau yz, which is equal to tau zy. Yeah. And of course, I'm not showing the stresses on the other faces that are hidden. So on the back, bottom, and on the other side, we have stresses that are balancing the ones that you saw on these three faces, but I'm not showing those ones. So essentially, here in this generic case, you have 6 independent components of stress. So all put together, you have 9 components of stress, and only 6 of them are independent due to equilibrium. This is called a tensor. Stress is a tensor. So tensors, they follow certain rules for transformation. Scalar is a tensor, but this is scalar is a 0th order tensor, like temperature. Okay. Vectors are first order tensors. Examples of vectors are like velocity or acceleration or displacement vectors, and they have certain rules for transformation. Stress is a second order tensor. We are going to see another second order tensor, which is called the strain tensor. We can write the components of the stress tensor in a matrix like this. In this matrix, the diagonal terms are the normal stresses, and the non-diagonal, they are shear. So here we have xy, here we have tau x, z. Yeah, and here we have tau xy again. So this is tau yx, which is equal to xy. And then diagonal term is sigma y. And here we have tau yz. And then moving to this one, this is tau zx, which is equal to tau xz. This is tau zy, which is equal to tau yz. And again, the diagonal term here is the other normal stress, which is sigma z. This is in matrix format, but we can also write it in a vector format. We can write this matrix in a vector format. You know, in this matrix, we have only 6 independent components, so that vector has only 6 members. That is called the void notation, which would look like this. So you can imagine here we will have all the normal components, so sigma x, sigma y, and sigma z, and then we will have the shear components, so tau xy, tau yz, and finally tau xz. As I mentioned, strain is also a second order tensor, which we can write it in with a similar format. So in a matrix format, strain can be written like this. So you can have normal strain, which we often show with epsilon. So we can have epsilon x. This is the normal. On the diagonal region, we write these ones. And then we also have the shear, right? We have the shear strains. So here we have gamma xy divided by 2, and here we have gamma xz divided by 2. And then similarly here you have gamma yx, which is equal to gamma xy divided by 2. We have epsilon y, and here we have gamma yz divided by 2. And then here we have gamma xz or zx, they're equal to each other, divided by 2. Gamma zy or yz, they're again equal to each other, divided by 2. And then finally the other normal strain, which is epsilon z. You may have noticed that here I'm dividing gamma by a factor of 2. You need to do that in order to have a tensor, so that this tensor can follow those transformation rules. But when we write this in the void format, the vector format, we avoid that division by 2 of the shear component. So here we have epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma xz. So you see we have corresponding vector of strains, and here we have vector of stresses. So here we have the vector of stresses, 6 independent components, and vector of strains, 6 independent components. You know that we can link these two with each other by using the material model or the constitutive model. So the simplest model that we know of is the linear isotropic, where by using Young's modulus and Poisson's ratio, we can link stress and strain. But the material can be more complicated, like composites, orthotropic, or other responses like nonlinear. So in general, we write that function like a matrix E, which is our constitutive equation, okay? Or we can write this as the vector of stresses equals our constitutive model times our vector of strains, okay? So that is how we would link our stress with our strain. But what else we know from solid mechanics is that our strain can be determined by using the displacement field. So you know, displacement field in structural mechanics refers to displacement of every point within our medium in x, y, and z direction, which often we show with u, v, and w. So the way actually they are linked is that epsilon x is du dx. So that's the derivative of displacement in x direction by x. Similarly, epsilon y is dv dy, and you can imagine epsilon z is dw dz, okay? And similarly for these shear strains, we can use derivatives to find them. I'm not going to write all of this, but I'm going to write everything in a matrix format. So if we have the vector of strains like this, so that would be epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma xz, right? So I'm going to write this in a matrix format. So here I have a matrix that includes all the derivatives that I just mentioned. And then I have another vector here, which is the vector of displacement. So u, v, and w. So displacement of every point in x, y, and z direction. So you can imagine here on the diagonal term, here we will have d, dx, and 0, 0, right? So if you multiply that by this, it just gives you du dx equals epsilon x. And then this one would be d dy, and this is 0. And then this is 0, 0, d dz. Okay, now when it comes to the shear strains, this will be d for the first one. So just make sure I'm doing it right. So this will be d dy, d dx, and 0. So this will be du dy plus dv dx, and this one is 0. So that gives you gamma xy. Next one, yz. This is 0, and this is d dz, and this is d dy. Okay, so that will be dv dz plus dw dy. And the last one, so I need to extend this a little bit further down here just to accommodate the last one. That one is d dz 0 d dx. Or neatly we can write it as vector of strains equals this matrix, which is the matrix of derivatives times the vector of displacements. We can use solid elements to predict the components of the stress and strain tensors. For example, for the gripper bone that we have solved previously, we can plot the contours of different stress components. We have 6 independent stress components at each solid element. So you can see them that I have plotted sigma x. This is the normal stress in x direction, y direction, z direction, and the shear stresses in different directions. And these are all straight output from the finite element solution of this structure. So as I said, we have 6 independent components of stress at each finite element. Then the question is, how can we determine that the element has reached failure, which means it has passed the ultimate strength. In other words, at each element we have 6 stress components. So which of these should be compared with the ultimate strength to decide if that element has reached the failure limit or not? So before going to answer that question, we need to learn about principal stresses. I mentioned that stress is a second-order tensor that follows certain transformation rules. Here we have the stress tensor written in the matrix format. And you know that if we have a matrix like this, we can find the principal components of that matrix. In other words, we can consider this as an eigen problem and then find the eigenvalues. By doing so, we can transform this matrix into another matrix that has only the principal components, which will be the components that are on the diagonal. Yeah. So I have done a transformation here, found the eigenvalues of this tensor, this matrix, and now these eigenvalues are written sigma 1, sigma 2, and sigma 3, and the rest of the components are 0. So what does that physically mean? It means that if you rotate that infinitesimal element that has the generic stress state with all 6 independent components non-zero, you can obtain an orientation for this cube, for this infinitesimal element, where you will have only the normal stresses and the shear stresses will be 0. So imagine if I rotate it enough, then it will end up in a new rotation that perhaps looks like this. And now in this new orientation, our axis, you can see that our coordinate system has rotated. So imagine the coordinate system now would be something like that. Yeah. And then here we have our stress components that are applied to our system. So if this was axis 1, axis 2, and axis 3, we have the principal component or principal stress, sigma 1 on this face, sigma 2 on this face, and then sigma 3 on this face. And then all the shear stresses are 0. These stresses, the principal components of that matrix, these are called the principal stresses. And the maximum value of these stresses is called the maximum principal stress. So here, convention is that sigma 1 is always bigger or equal to sigma 2, bigger or equal to sigma 3. So now you can see we have found our maximum principal stress, which physically means it is the maximum value of the normal stress at any given point within our medium. You will see that this is actually useful definition when we are looking at failure criteria. For instance, for brittle material, most of the time we use this tensile normal stress in order to decide whether the stress has reached, the stress state has reached a magnitude and intensity that failure would occur in our brittle material, and we call that one the maximum principal stress criterion. Well, the shear stress also has a maximum value at every point inside our medium. We can show that the maximum shear stress equals the difference between the maximum and minimum principal stresses divided by 2. The difference between the maximum and minimum principal stresses is called the stress intensity, which is 2 times the maximum shear stress at that location. Well, another concept is introduced here. We can decompose the stress tensor into the volumetric and volume preserving components. These set of stresses do not produce any change in the volume of the element. They can only distort the element's shape. And these set of stresses can only change the volume of the element. They cannot distort the shape of the element. An example of these stresses or this stress state is hydrostatic pressure, like placing this cube or metal cube down in the ocean. In fact, it is shown that if you put a metal cube down in the ocean, it will not fail no matter what is the hydrostatic pressure. The von Mises stress, also called the equivalent stress, incorporates the deviatoric stresses only. It is obtained by equating the elastic energy stored in an element subjected to volume preserving or deviatoric deformation in the following states: the triaxial deviatoric stress and the uniaxial deviatoric stress state. This leads to this equation for the von Mises stress as a function of the principal stresses sigma 1, sigma 2, and sigma 3. So essentially, the von Mises stress incorporates the deviatoric deformation of an element. We usually use the uniaxial tension test to determine the strength of materials. So here I'm showing a uniaxial tension test, and this is an element taken at this cross section, and we know that this element is subjected to two stresses only, and these are normal stresses. S here can represent the yield or ultimate stress of the material. For this uniaxial stress state shown here, the maximum principal stress equals the stress intensity, or 2 times the maximum shear stress, and they equal the von Mises stress. Hence, if any of these stresses are larger than S, we predict that the structure fails under uniaxial tension. However, for the general stress state or triaxial stress state, these three quantities are not equal. So in a most generic condition, the maximum principal stress is very unlikely to be equal to the stress intensity and unlikely to be equal to the von Mises stress. So the question is, which one of these three should be used and compared with S to predict the failure of the structure? Well, the fact is that the failure criteria are tailored to material types. So what do I mean? For brittle materials like concrete and thermosets, usually the maximum principal stress criterion is used. So what is maximum principal stress criterion? It's this. So material fails if the maximum principal stress is larger than ultimate strength of the material. And you know that this is a field. So you have the distribution of sigma 1, and where this sigma 1 in the structure is larger than this, that is where the failure starts from. For ductile materials like steel, we usually use the von Mises or stress intensity criterion. And these are the criteria. Von Mises criterion is when von Mises stress is larger than the yield strength, and the stress intensity criterion, also called Tresca, is when the stress intensity is larger than the yield strength. You should also note here that the Tresca criterion is more conservative than the von Mises criterion. This means that you will be more conservative in the design, but probably your design will be a bit heavier by using the Tresca criterion. So as I mentioned in the beginning, like 50 to 90% of all mechanical failures are due to fatigue. So fatigue, you can imagine, it applies loads on a structure like this bar, this beam, continuously, and potentially it reverses the direction of the load. But this can happen for thousands, hundreds of thousands of cycles until fracture starts. Especially fracture starts in materials and structures where there are stress raises. So if there is a notch, for instance, that is where there is a stress raiser, and that is the location where a crack and fracture can initiate from under cyclic loading. So if I want to show a cyclic loading, imagine in the rod I was showing there. So if I look at the maximum bending stress in time, so this axis is time and this axis is the stress. So I was applying loads and reversing the load. Okay, so the load was going to a maximum and going back, so reversing it again, going to a maximum, to a minimum, maximum, minimum, and then this can continue for, as I mentioned, thousands or hundreds of thousands of cycles. Imagine like a bicycle, a crankshaft, how many times you pedal. That is when you're applying this cyclic loading on the structure. So the reality is that under cyclic loading, then the failure of the structure can occur before even the load reaches the strength, yield, or ultimate strength of the structure. So having the structure under the cyclic loading essentially means that will weaken our structure. So we can run experiments on structures and apply this cyclic load. So we keep the load at a certain level, at a certain threshold, and we apply the load until it breaks, and then we change the load, either increase or decrease it, and again we do that, and so on. And then we can draw another diagram which has this load that I mentioned. We call it S. This is the load that we are controlling, so we are increasing the peak of this load gradually, and then at each fixed value of that we continue the cycles until it breaks. And we can have on this axis the number of times that we are applying that cyclic loading. So imagine if we had fixed this value at this magnitude, and then we apply the cyclic loading and it fails at this number of cycles, then we have a point here. And then we continue that. So of course, when the magnitude of the load that we are applying is larger, the structure can sustain smaller or fewer number of loading cycles. But if that magnitude is lower, then it can sustain more number of cycles. So if you do that, then you will see that we will have a curve that could look like this. Okay, so we call this curve an SN curve. So imagine for one material, let's say material A, this would be the SN curve. If we have another material, we can run similar experiments, and by running that experiment we can again draw another SN curve. So imagine for another material we could have an SN curve that would look like this. Okay, so let's call it material B. So you can see material B essentially has higher resistance to fatigue. One interesting aspect here is that, as you see here, as we are increasing the number of cycles, it looks like material A actually, its fatigue life, it approaches zero. But in material B, it looks like it doesn't actually approach zero, and it plateaus here. So there will be a distance between zero. In other words, if you apply these loading cycles for infinite number of times, this structure will never fail. So that is what we call the fatigue life. So this is called the fatigue life of the structure. So for structure B, the fatigue life has a certain magnitude. For A, fatigue life is zero. So if I then want to know at what level of stress these structures will fail for a given number of cycles, so if I get like these cycles, then I can go on the y-axis and determine the magnitude of S. And as I mentioned, B has higher resistance because it will fail on the larger value of this alternating stress when we are applying the cyclic loading. Now we are going to look at different types of cyclic loading. But before doing that, we should consider that at every point in our structure, as I mentioned, we can have this infinitesimal element, and we have a stress state at that point, which is determined and defined by the stress tensor. So here I have our stress tensor. But then, of course, the question is that this one has 6 independent components. Which of these we are looking at when we are talking about this cyclic loading? Is it like sigma x that is having cyclic loading? Is it tau xy? It can obviously get really complicated, but don't worry. We have already learned about failure criteria, so we can use our criteria to come up with an equivalent stress out of these 6 components. So essentially we put this into our failure criteria. So let's call it function f, and that gives us something that we call sigma. So this is our equivalent stress. This can be the von Mises stress, this can be the maximum principal stress, this can be the stress intensity. It depends on the material that you are looking at. Okay, so far this is combined together the stress tensor to give us one equivalent stress. Now, when we have this cyclic loading applied to our structure, this sigma is going up and down, but this trend can have different shapes. I'm going to show you 3 different types of loading. One of them would be, so here I have the time axis, and here this one is the sigma axis. So that is the value of sigma. And in time, this stress can go up to a maximum value and go back to 0, go up to a maximum value, back to 0, go up, back to 0. All right. And this is the max. This is the mean, and I mean minimum, and this one will be the average or mean. Okay. So this one is called the zero-based loading condition, which often we show with a quantity r equals 0. So this is a zero-based. We can have another type of loading where we have our time and we have our stress axis, and this time that stress is going to a maximum value which is positive and a minimum value which is negative. Essentially we are alternating our stress. So this is the max, this is the mean or minimum, and mean here or the average stays at 0. So this one is called fully reversed, and for this one that r value is -1. And the third one is a condition where we have the time axis, we have our stress, and we have a mean or average value for our stress that always remains above 0. So something like this. So here that would be our maximum, this would be our minimum, and this is our average or mean. And in this situation, r is bigger than 1. Okay, well, I did mention r, so it does have a definition which I'm going to show here. So first of all, we have the so-called alternating stress. So that one we show with S, and I'm sure this is now familiar to you. So this is defined as sigma max minus sigma mean divided by 2. So essentially it is that magnitude we are looking at. Yes, that is the magnitude, the amplitude of the vibration about the base. And then we can also have the mean or average, which I showed there on the plots, and that is really the average of max and mean. So that divided by 2. And then last one, which is R, this is called the stress ratio. R is defined as sigma mean, so the minimum value of sigma divided by sigma max. So now you can see why R was 0 here, because sigma mean was 0. R was -1 because sigma mean magnitude equals sigma max, but it's negative, so it's R -1. And in this condition, of course, this is giving us a value for R that is bigger than 1. So these are the 3 different loading conditions that we often are dealing with a simple definition of fatigue analysis. So just a bit of correction here. So in this situation, both minimum stress and maximum stress are bigger than 0. So min divided by max, it actually gives us R bigger than 0. So this is the correction I need to make. The mean stress or the average stress can have a significant effect on increasing the damage caused by cyclic loading. The SN curve shown here, it shows this effect by lowering the SN curve as the mean stress is increased. You can see as we're increasing the mean stress, this SN curve is reduced. However, we usually do not change the SN curve. Instead, we increase the alternating stress by using certain equations. So here I have shown 2 methods. One is the Goodman method, which is usually used for brittle materials, and we can find the corrected alternating stress by using this equation. SU is the ultimate strength, and S is the alternating stress from this equation. The other method is called Gerber, and this is suitable for ductile materials, and the equation used for Gerber is this. Well, now let's solve a practical problem. This crank arm is under a zero-based cyclic load, so it means the load goes from 0 to maximum back to 0. The maximum load is 500 newtons. It is perpendicular to the crank arm, so in this direction, and at a 10 centimeter distance from the center of the hole where the pedal is connected to the arm. So this is the hole. So from the center of this hole, it's located at 10 centimeters from this center. So what you need to do is to determine the life cycle of the crank arm, assuming that it is made of aluminium alloy. I have solved this problem in a supplementary video, which I invite you to watch to see how the theory that we have discussed so far can be used when we are setting up our simulation and interpreting the results. So in summary, we have learned about principal stresses, maximum principal stress failure criterion, von Mises failure criterion, the Tresca failure criterion, so 3 main failure criteria, fatigue failure, and we learned what is an SN curve, and we also found out about the important effect of the mean stress, and that we need to use mean stress correction methods when the mean stress is non-zero. I hope you have enjoyed this lecture. Thank you for your attention.